So before we actually study what Dalton's law of partial pressure actually is, let's go through a couple of illustrations, examples, and cases. Once we have understood it based on the illustrations, then we will move to the definition. Yeah. So let's say you have a cube here. It has, let's say, gas A or gas 1, whatever you want to call it, right? They are moving randomly, colliding with each other and the walls of the container. Okay. Then you have another gas, let's say gas red or gas B or gas 2. Okay. Then you have a third gas, right? Okay. Now what are we going to do here is we're going to combine all three of them in the same fixed volume. Now one thing that we need to properly understand here is that when we talk about volume V, right? It is not necessary, the volume occupied by the particles. No. In fact, later in the session today, we're going to learn that V volume is essentially equals to the volume available to the particles for moving around and making collisions. Right? So the V volume here is essentially the volume that is available for the particles to move around randomly and do its collisions. That is the V volume in PV equals to nRT. That's one thing. Second thing is that you are supposed to, when you call them as ideal gas, this also we will study later in the session today under the topic kinetic theory of gases, that when you consider ideal gases, right, you're basically, taking each and every individual particle to be a point mass, as in it's a single point. That is, the volume of an individual particle is assumed to be negligible, right? That is the radius, the molecular diameter, the size of an individual particle is neglected. It's assumed to be a point mass, right? I think if you move to the conversation in physics regarding center of mass and everything, right, this conversation will make a lot more sense. So that's another thing. Now, why are these points important? So let's take an example. Let's say you have a football field, right? And let's say the players are moving around. Let's say this team A and team B. Tell me something. During the game, what area of the playground is available to the team A players as a whole? Well, the entire field, right? Not just half of the field. They can move around, collide in the entire field. Similarly, what is the case with the other team? They also do not have, not in capitals. They also do not have half the field. They have the entire field for moving around and doing their motion. So when we take this particular example, right, and we try to write the equation for pressure, the volume that we consider is not just V by 3 because there are 3 gases. No. Or, in their respective proportions, the volume is divided. No. Because for gas 1 or gas yellow or blue or whatever that was, right, the entire volume of the container is available for moving around and making collisions. So in the denominator, we have the entire V. Here we have its number of moles, and all of 3 of these gases are taken currently at the same temperature. Similarly, if you develop the equation for P2, this is what you have, and P3, this is what we have. Now on the next page, I'm going to do some calculation, but I want you guys to do that calculation in your head. What am I going to do? I want you to combine P1, P2 and P3. What's going to happen? P1 plus P2 plus P3. What's going to happen? RT taken common out. 1 by B taken common out. What do we have over here? We have P1 plus P2 plus P3 is equals to N1 plus N2 plus N3 whole multiplied by RT by V. Right? And what is N1 plus N2 plus N3? That is equals to what? N total number of moles, right? So what do we have over here? We can also write that as that P total, or in fact, why am I writing? I'm usually lazy. I don't know what has happened to me. Yeah, okay. Okay, so this is also what we can say we have, don't we? Right? Okay. So let's get now back to the definition of partial pressure, right? What is partial pressure essentially, right? So if you have a mixture of n number of gases, right? The total pressure, think about it, right? Think about it. In fact, you know what? Let's forget the definition again. Let's think of in terms of those cubes. Let's say this cube was there, right? It has the yellow gas, the blue gas, the red gas. Now consider that all the red particles are colliding, right? They collectively must be applying some force on this wall. Divide that force total by the area. That's pressure because of the red gas. Similarly, do the same exercise for yellow particles. All the yellow particles collectively applying some force divided by the area of the wall. That becomes pressure because of the yellow gas, correct? And similarly, you can do the same exercise for blue as well. I forgot which one was 1, which one was 2, and which one was 3. So let's not get into that. Yeah? Okay. But you get, right? 3 gases were there. Their individual collisions, right? Their individual but respective. Like, so all the yellow collisions divided by the and the total force applied because of them divided by the area, that's become pressure because of the yellow gas. And so for the red and so for the blue as well. Right? Now, if you consider this wall has red particles colliding, yellow particles colliding, blue particles colliding. So what is the total pressure on this wall? The total force because of all the yellow plus the total force because of all the blue plus total force because of all the red, whole divided by the area. And that is exactly what we had, don't we? That the total pressure is equals to the individual pressure of the constituent gases combined. And this constituent gas, that is pressure because of only a particular gas in the mixture, is called as partial pressure. So the pressure on this wall because of the yellow gas is called as partial pressure of the yellow gas. Pressure on this wall because of the red gas is called as partial pressure of the red gas, and so you can also call it for the blue gas as well, right? Total pressure of the mixture is the summation of partial pressure of each component gas. So the partial pressure is that individual component for a non-reacting mixture, because we don't want them to react, right? Because let's say you have 1 mole of N2, let's say you have 3 moles of H2. Under the under specific conditions, they might react and give you some NH3, and you might not end up with a total of 4 moles. 1 plus 3, you might end up with some other amount of moles, right? Because some amount has been converted into NH3. Yeah, so that's where it gets tricky. So yeah, for non-reacting gaseous mixture, I think we clarified this in the beginning as well. You can further look at this, right? So what do we have? We have O2 gas, we have N2 gas, and basically they are not reacting at the specified temperature. This basically applies a 159 millimeters of Hg pressure. Remember, millimeters of Hg is indeed a pressure unit. N2 applies 593 millimeters of Hg pressure. So the total pressure when in the same volume, pistons are fixed, right? Basically, when both of those gas are somehow compressed and accommodated over here, the total pressure turns out to be a simple summation of the two individual pressures, right? Okay. Now, one teeny tiny little concept, right? So let's take this example. We have pressure of the one, that is partial pressure of gas 1 divided by total pressure, right? Okay. Let's do this thing over here. What is partial pressure of 1? N1 RT by V. Correct? Okay. What is the total pressure? Total number of moles RT divided by V, right? This is capital V. Okay. These two things cancel out. These cancel out. What do we have? N1 by NT. What is this? Mole fraction of the gas 1. Similarly, P2 by PT becomes essentially what? Mole fraction of the gas 2. And you have, if you have not just 2 gases, let's say you have 10 gas combination, 15 gas combination, like atmosphere, right? So basically, the partial pressure of the nth gas divided by the total pressure will be the number of moles of the nth gas divided by the total number of moles of the nth gas divided by the total number of moles. That is the mole fraction of the nth gas, right? You realize this is the entirety of partial pressure concept. Partial pressure concept is done. Yes, indeed, partial pressure concept is done. So simple, right? You understand? Okay.
For more videos and live lectures on the JEE, click on the subscribe button now.